In this video, we will discuss about Bernoulli's theorem and Bernoulli's equation in fluid dynamics. Bernoulli's theorem, also known as Bernoulli's principle, states that the total mechanical energy of the moving fluid, which includes gravitational potential energy of elevation, fluid pressure energy, and kinetic energy of fluid motion, remains constant. The Bernoulli equation applies to various measuring devices like venturimeter, orifice meter, pitot tube. Bernoulli's equation formula is the relationship between pressure, kinetic energy, and gravitational potential energy. So here is the formula, where P is the pressure exerted by fluid, V is the flow speed, ρ is the density of fluid, height from the ground, that is small y. Now we will see how to derive Bernoulli's equation. Consider a pipe with varying diameter and height through which an incompressible fluid is flowing. Let's assume the energy system we are considering is composed of volumes of water 1 and 2 as well as all the fluids in between those volumes. The areas of cross-section represents as A, the flow speed represents as small v, height from the ground, that is small y, and pressure P at two different points as shown in figure. Assume the density of incompressible fluid remains constant at both the points and energy of fluid is conserved as there are no viscous forces in the fluid. If we assume the fluid flow is streamlined, non-viscous, and there are no distributive forces affecting the flow of fluid, then any extra energy added to the system will be caused by the external work done, that is dW, on the fluid from pressure force surrounding it. First we'll try to find the external work done on the water, that is dW. None of the water between point 1 and 2 can do external work since that water is all part of our energy system. The only pressures that can directly do external work on our system are P1 and P2. Work can be found with the formula, that is force into distance. Therefore, the work done on fluid is given as dW equal to F1 dx1 minus F2 dx2, where force equal to pressure into area. Here the water to the left of volume 1 will do positive work since it forces in the same direction as the motion of fluid. Here the water to the right of volume 2 will do negative work on our system since it pushes in opposite direction as the motion of fluid. Therefore, dW equal to P1A1 dx1 minus P2A2 dx2. For simplicity, we will consider the case where the force from water pressure to the left of volume 1 push volume 1 through its entire width dx1, assuming the fluid is incompressible. This must displace an equal volume of water everywhere in the system, causing volume 2 to be displaced through its length dx2. Here, the terms A1 dx1 and A2 dx2 have to be equal since they represent the volumes of fluid displaced near point 1 and 2. If we assume the fluid is incompressible, an equal volume of fluid must be displaced everywhere in fluid, including near the top. So A1 dx1 equal to A2 dx2 equal to dV. This simplifies the left side of work energy formula. Now we have to address the left hand side of this equation, where change in kinetic energy of the fluid is given by this equation and the change in potential energy is given by this equation. So I will substitute all the obtained values in equation, and after rearranging the above equation, we will get Bernoulli's equation.